Hi, I'm Mark, and today I'd like to tell you about our new data structure for encoding triangulations of surfaces. The reason that we're interested in encoding triangulations of surfaces is that, quite frankly, triangle meshes can be very frustrating. Consider these two meshes, for example. If we just think about them as surfaces in space, they're both fine. They're manifold, they're intersection-free, and essentially as nice as surfaces can be. But if we look at them as triangle meshes again, things change. The mesh on the left is still great. It's nice and smooth, and all of the triangles are pretty well shaped. But the mesh on the right is terrible. It's full of these sliver triangles that are just waiting to cause numerical issues. And indeed, geometry processing is full of great algorithms that work perfectly well for the mesh on the left, but produce essentially nonsense for the mesh on the right. Even though the mesh is a fine representation of the geometry of this surface, it just isn't amenable to higher level computation. Today, I'll show you a new data structure that lets us escape this frustration and offers a new guarantee of correctness. The trick is to use integers to efficiently encode a high-quality intrinsic triangulation. Recently, there's been a lot of work on remeshing algorithms to generate high-quality meshes of poorly triangulated domains. The state of the art now can fix up some truly horrible meshes. However, these algorithms are volumetric in nature, rendering them at least an order of magnitude slower than traditional 2D meshing. And fundamentally, such approaches to remeshing need to make a trade-off between mesh size, mesh quality, and geometric fidelity. Hence, instead of extrinsic remeshing, we consider intrinsic triangulations. This technique allows us to sidestep the trade-offs of extrinsic remeshing, providing triangulations that massively improve triangle conditioning while preserving the geometry exactly and not increasing the mesh size too much. The secret is to allow triangles to bend in certain ways along your surface. The mathematical fundamentals date back to the mid-20th century, but intrinsic triangulations have become increasingly popular in recent years as a simple and efficient approach to robust geometry processing, finding applications in parameterization, surface editing, and spectral filtering, amongst other things. When working with intrinsic triangulations, you often need to keep track of how these intrinsic triangles sit on top of your original mesh. To date, there are two data structures for this task. The first option is the overlay mesh, which explicitly keeps track of a common subdivision that contains all original and intrinsic edges. This works, but simple edge flips become non-local and expensive, and no further mesh operations were ever described. On the other hand, there's the signpost data structure, which represents intrinsic edges via floating point signposts. This opened the door to a wide variety of local mesh operations, but it entrusts the connectivity of the common subdivision to floating point, which often causes errors on low-quality meshes. Our new integer coordinates data structure offers the best of both worlds, providing efficient local mesh operations while also guaranteeing a valid common subdivision. To do so, our data structure builds on the idea of normal coordinates, a concise representation of curves and surfaces from the field of geometric topology. Again here, the core idea dates back to at least the mid-20th century. Since then, normal coordinates have proved useful in computational topology as an efficient encoding scheme for curves, but have only recently begun to see use in geometry processing. The great thing about normal coordinates is that they're extremely robust. Topologists regularly use them to study absolutely abysmal triangles in thought experiments like, imagine I took my cup of coffee and drew a bunch of triangles on the top. What would happen to those triangles if I swirl my coffee? This process may mangle the triangles beyond any human recognition, but normal coordinates can still encode them perfectly well. However, normal coordinates don't work out of the box as a representation of intrinsic triangulations. There are three fundamental difficulties. First, topologists generally don't care about the specific path the curve follows. It'll take a little bit of work to pin down the exact curves we want to represent. Secondly, we want to perform a wide variety of local mesh operations, but traditionally normal coordinates only support edge flips. And finally, there are ambiguities that arise when you try to identify logical mesh edges with curves stored in normal coordinates. In this work, we propose a robust new data structure for intrinsic triangulations, which combines normal coordinates with additional integer roundabouts. Our data structure supports a wide variety of local mesh operations, and as validation, we implement a recent intrinsic retriangulation algorithm, and we prove quality bounds on the resulting triangulations. Finally, we also introduce a new procedure to optimally transfer functions between different triangulations of the same surface. Note that our goal here in all of this is not to introduce new applications or algorithms for intrinsic triangulations. Rather, we provide a new data structure that supports all of the existing applications and algorithms, but performs far more robustly due to its greatly reduced dependence on floating point. Okay, now let's dive in. We'll start with a basic question. Consider this curve in the plane. How would you represent it? One natural choice is just to pick some points along the curve and connect them in a polyline. This is a straightforward representation to work with and familiar to many of us. The downside is that it relies fundamentally on floating point. Now, for a nice curve like this in the plane, this is not a problem at all. However, we eventually want to work with curves that lie along terrible meshes, in which case the dependence on floating point can actually cause all sorts of errors. Hence, we draw upon a very different approach, normal coordinates. Topologists imagine that instead of just working in the plane, we have some triangulation of the plane that our curve sits on top of. Then, we simply count how many times our curve intersects each edge of the triangulation. It's that simple. In order for normal coordinates to encode our curve properly, the curve has to follow two simple rules. First, it isn't allowed to cross itself. And second, it isn't allowed to make U-turns. That is, it can never enter a triangle and then immediately exit via the same edge. Looking at our curve, it obeys both of the rules, so we're good to go. At this point, you might be wondering how much these crossing counts can really tell us about the curve. For one thing, they clearly can't determine the curve's exact geometry, since we can apply a small deformation to the curve without changing the normal coordinates. However, the deformation does have to be small. If we perturb the curve so much that it crosses a vertex of the triangulation, then a bunch of our normal coordinates really must change. Another way of saying this is that our deformations cannot change the sequence of triangles that the curve passes through. But modulo these small deformations, normal coordinates really do determine our curve. To see why, let's forget the trajectory of the curve for a moment, keeping only the normal coordinates and the endpoints, and let's try to reconstruct it. If we look around from the left endpoint, we see that there's only one edge nearby that the curve ever crosses, so it must start off heading in that direction. Crossing that edge brings us into a new triangle, and again, the curve only ever crosses one other edge, so we'd better head off to the right. Now we enter the next triangle, apply the same reasoning, and continue to the right. But now, as we enter this new triangle, we notice that at various points in time, the curve actually crosses all three of this triangle's edges. So how do we know where to go? Well, let's zoom in and see what we can find out. The normal coordinates tell us that the curve crosses the top edge once, the right edge once, and the bottom edge twice. We don't know exactly where these crossings happen, but we can just draw them in arbitrarily to help us think through the situation. Now, given these four crossings, the problem of determining where our curve goes boils down to picking a way of connecting these crossings together. In our case, there are three possible options. We can connect them vertically, with an X, or horizontally. Now, remember our two rules. We made sure that the curve never crosses itself, so we definitely shouldn't connect up the crossings with an X. And similarly, the curve never makes a U-turn, so we can't use the bottom option either. This leaves us with only one option, and we conclude correctly that the curve must head downwards. In the next triangle, the same thing happens. At various points in time, the curve actually crosses all three of the triangle's edges. But if we zoom in and draw the crossings, we find that there's only one way to connect them up without making a U-turn and without creating intersections. Indeed, by following our rules, we can trace out the rest of the curve without issue. The key point here is that we can recover the general path that this curve takes from its normal coordinates, although we still don't know the curve's exact geometry. Now, if we have a mesh with normal coordinates on it, we can use them to trace out a curve along the surface in exactly the same way. But, as before, this curve is only defined up to small deformations. There are a bunch of other curves which are all compatible with the same normal coordinates. So how do we know which curve to pick? Well, one good choice is just to output the curve that bends the least. This is, in some sense, the nicest curve we can pick. And while it may seem kind of arbitrary at first, picking the curve that bends the least turns out to work extremely well. The main benefit of this is that if we start with a curve which is already as straight as possible and read off its normal coordinates, these actually encode the geometry of the curve. We can recover its trajectory exactly from the normal coordinates alone. So it turns out that if you want to encode a straightest path along your surface, you don't need floating point at all. You can encode it exactly using integers. Now, let's say that instead of a single curve, you have a whole collection of straightest curves that you want to encode. You could store individual normal coordinates for each curve, but this quickly becomes very expensive. Luckily, there's a better way. All we have to do is count how many times any curve intersects each edge. As long as the curves don't cross themselves or each other, this single set of normal coordinates determines the geometry of all of our curves at once. We can take any network of non-crossing straightest paths and represent it exactly via normal coordinates. And the edges of an intrinsic triangulation are precisely a network of non-crossing straightest paths. So we can store all of these edges using just one integer per mesh edge. However, there's still a subtle problem preventing us from using normal coordinates to fully encode an intrinsic triangulation. Let's say you have this mesh of a tetrahedron and you're storing a second triangulation sitting on top of it. You then extract this curve running along the surface of your mesh. Well, this curve corresponds to some logical edge in your second triangulation, but it's not immediately obvious which edge that is. Now, you might point out that this edge connects vertices I and j, but unfortunately, our intrinsic triangulation here actually has two distinct edges from I to j, so it's hard to tell which of the two logical edges you've just traced out. In some prior work earlier this year, we introduced a new notion of roundabouts to handle this ambiguity. The basic idea is that around each vertex, we assign local indices to the edges of the second triangulation, starting at some arbitrary but fixed edge. Then, for each edge of the underlying triangulation, we record the index of the next edge in the second triangulation. So now, if we trace out this pink path, we can observe that it comes right after this black edge, which means that we must have traced out edge number 1. And similarly, if we trace out this pink path instead, we observe that it comes one after the previous path, so we must have traced out edge 2 this time. In this way, roundabouts completely resolve the ambiguity around traced edges, and all we have to do is store one more integer per oriented edge. Now that all the pieces are in place, let's discuss the integer coordinates data structure. First and foremost, we need to keep track of the connectivity of the intrinsic triangulation, which we do with an ordinary mesh data structure. Then, we track how these intrinsic triangles sit above our input mesh using normal coordinates and roundabouts. And finally, like the other intrinsic data structures, we store the lengths of intrinsic edges and barycentric coordinates for inserted vertices. Using this representation, we can perform several important mesh operations. Since the normal coordinates and roundabouts are the new part of this data structure, we'll focus on how they get updated. When we flip an edge, we have to compute new normal coordinates and new roundabouts for this flipped edge. Both tasks can be done by simple formulas, depending only on the old normal coordinates and roundabouts. Amazingly, neither expression depends at all on the geometry of our triangulation. We just have to perform two constant time arithmetic calculations. Now, suppose we want to take some face of our triangulation and insert a vertex into it. We insert the vertex and 3 adjacent edges, and we have to compute new normal coordinates and roundabouts for these edges. Note that unlike the flip formula, our new normal coordinates and roundabouts now really do depend on the geometry of our triangulation. For example, if we'd picked a different location to insert the vertex, we would have obtained different normal coordinates on the new edges. However, this poses no essential difficulty. Here's what we do. First, we trace out the second triangulation's edges along our surface to determine where these crossing curves are. Then, we compute which region our newly inserted vertex lies in via a few line-side tests. Once we know this region, we can easily determine the new normal coordinates, and we can compute the new roundabouts using the same calculation we use following an edge flip. Finally, suppose we want to remove a vertex. Now, I should point out that we generally cannot remove vertices which were present in the input mesh, since that would distort the geometry. But we are free to remove any vertex which we previously inserted. If the vertex has degree 3, then it's very easy to remove. All we have to do is delete it from the mesh. This leaves behind a flat triangular face, and no normal coordinates or roundabouts even need to be updated. If the vertex does not have degree 3, we can simply flip edges until it does, and then remove it. The final operation that we offer is computing the common subdivision of our two triangulations. The common subdivision, also known as the supermesh, is simply the polygon mesh that you get if you cut one triangulation along the edges of the other. Notably, any piecewise linear function on either mesh is also a piecewise linear function on the common subdivision. This makes the common subdivision a sort of bridge between two triangulations, relating functions on one to functions on the other. Concretely, we compute the common subdivision by cutting each face of our underlying triangulation along any edges of the second triangulation that cross it. Importantly, the connectivity of the common subdivision depends only on our normal coordinates, and is therefore protected from floating point error. Now, let's briefly discuss some applications. First, we'll look at retriangulation. In the plane, there's a classic tool called Delaunay refinement, which efficiently computes meshes with guaranteed quality bounds. This algorithm is used throughout computational geometry and simulation to produce high-quality planar meshes. Using our data structure, we can implement a recently proposed intrinsic version of Delaunay refinement. Here, our data structure acts as a drop-in replacement for the signpost data structure. We also prove, for the first time, that intrinsic Delaunay refinement produces triangulations with quality guarantees analogous to the planar case when run on meshes without boundary. And we extend the intrinsic algorithm to run on meshes with boundary, which were not previously supported. Unfortunately, we have not proven any quality guarantees on such meshes, but we found that the algorithm works well in practice. To validate our data structure, we computed intrinsic Delaunay refinements and the associated common subdivision on all of the manifold meshes in the Thingy10K dataset. Computing these Delaunay refinements was quite fast. On most meshes it takes less than a second, and there were only 6 meshes where it took over a minute, and on each of them it took only a few minutes. And we successfully obtained Delaunay refinements and common subdivisions on all of these meshes. For comparison, the signpost data structure succeeds on only 70% of meshes, and here's one representative example where the poor mesh quality causes floating point errors in the signpost data structure, whereas our integer coordinates produce the correct result. One key application of this retriangulation scheme is PDE-based geometry processing, such as the heat method for geodesic distance. This can yield very accurate results on high-quality meshes, but running the heat method on bad meshes often results in large errors. For example, the result on this chair looks nothing like a distance function. It's not even monotonic as you move away from the center point, and has a mean error of almost 30%. On the other hand, if we perform intrinsic Delaunay refinement before running the algorithm, we can drive the error all the way down to 2%. But once we have a high-quality solution on the intrinsic triangulation, what do we do with it? Generally, what we really want is a function on the input triangulation instead. One easy solution is to simply sample the values of the intrinsic function at the vertices of the input triangulation. This is straightforward to compute, but often yields a suboptimal result. Instead, we can try to pick the function on the input mesh, which is as close as possible to our high-quality solution on the intrinsic mesh. This sort of optimization is common in the extrinsic FEM literature, but we apply it to the intrinsic setting for the first time. Of course, the closest function depends on what error metric we use, but for L2 error, finding the closest function on the input mesh just boils down to solving a sparse linear system. As an example, we consider a Poisson problem over the unit square where we know the analytic solution. We generated a few thousand low-quality meshes of this square and tried to solve the equation. If we solve directly on the input mesh, we get bad solutions, and the error hardly even decreases as we increase the mesh resolution. If we solve on an intrinsic Delaunay triangulation and simply copy values back at vertices, our solutions get much better and converge as the meshes get finer. But moreover, if we instead take the L2 closest functions on the original triangulation, we get even more accurate solutions. As an application with a very different flavor, we consider the recent flip-out algorithm, which computes exact geodesic paths on surfaces via edge flips. Again, the algorithm works out of the box with our data structure and inherits our robustness guarantees. For example, on this soldier, floating point-based signposts fail to even connect 2 vertices, while our integer coordinates extract the geodesic with no issues. Finally, let's discuss some limitations and future work. One interesting direction would be to develop a hybrid data structure that maintains both signposts and integer coordinates. Although our integer coordinates support essentially the same set of operations that signposts do, signposts are sometimes more efficient. By carefully combining signposts and integer coordinates, one may be able to keep the robustness of our data structure while also offering the efficiency that signposts provide. Another interesting extension of the data structure would be to construct a truly integer-only encoding of intrinsic triangulations. While we greatly reduce the extent to which we rely on floating point, we still use it to store the lengths of our intrinsic edges. However, this is, in some sense, merely a performance optimization. You could, in theory, actually compute these intrinsic lengths as needed directly from the normal coordinates. Speaking more generally, we inherit the usual trade-offs of intrinsic triangulations. In particular, we exactly preserve the geometry of the input mesh, which means that we cannot coarsen the mesh, and we cannot repair spurious holes and handles. Overcoming these limitations would be tremendously useful, but would require some fundamental changes to the way we think about intrinsic geometry. And finally, although I've focused entirely on normal coordinates for curves today, the concept was originally developed to study surfaces embedded inside of tetrahedral meshes. It would be interesting to consider whether parts of this data structure generalize to higher dimensional meshes. Thanks for listening.